Hi students, Ms. Suchi here. We are covering lesson 6.3 in geometry. This is on arcs and angles. Our objectives today: I can discover the relationship between inscribed angles of a circle and its intercepted arc. So prior to this, we've learned about central angles and how central angles are the exact same size as their intercepted arc. So if we look at this first diagram here, we have this central angle right here. And we've got this funny little measurement here. That's just a Greek symbol representing another variable. For geometry, Greek symbols are often used for variables, but you can just put an X if that makes it more simple for you. But that central angle, let's say that it was, I don't know, 100 degrees. Looks like an obtuse angle to me. Then the intercepted arc would also be 100 degrees. That is information that we learned from a previous lesson. But now we're looking at the inscribed angle. And when we look at the inscribed angle, remember, it is the one where the vertex is on the edge of the circle, and then the sides make up chords. So here you can see our green Pac-Man mouth. It's eating towards that blue arc. But if I highlight the inscribed angle, let's highlight this one in pink, it is also eating towards that same blue arc. Notice the mouths, the green mouth and the pink mouth, they touch the same arc. But as we pull that angle back towards the edge of the circle, it actually becomes smaller. So here you can see that this angle obviously looks obtuse. But this pink angle, the inscribed angle, does not appear to be obtuse. It looks to be acute. And in fact, the relationship between the central angle and the inscribed angle, or the intercepted arc and the inscribed angle, is that this inscribed angle is half the size of the central angle or half the size of the intercepted arc. So in this example, my inscribed angle would be 50 degrees. Now this symbol right here, again, is another Greek symbol, just representing a variable. That one's more common for geometry. It's like a O with a slash through it. That's called theta. And that's often representing degrees or unknown degree measurements. So down here, we could do another example where we have a measurement for our central angle. The arc would be the same measurement, but then the inscribed angle would be half that size. So x divided by 2. So the measure of an inscribed angle is half the measure of the intercepted arc. Now, instead of intercepted arc, we could also say half the measure of the central angle. So I'll put or central angle, because the central angle and the intercepted arc are always the same size. Okay, great. Investigation number 2, inscribed angles intercepting the same arc. So here you can see we have an intercepted arc highlighted in blue. I am going to trace the two inscribed angles here. So AQB, I'm going to trace in pink. AQB. And then APB, we'll trace in green. APB. Now, if you notice, they both meet that same blue arc, AB. The exact same for both of them, where they open up and eat towards it. And they're both inscribed angles. So let's put in some measurements here to give examples of this. Let's say that this arc was 100 degrees. Now, I really don't know what the measurement is. I'm just throwing out a number as an example. If we were looking at the central angle would also be 100 degrees. But remember, when we pull it back to the edge, that inscribed angle becomes half the size of this arc. So that means angle Q would be 50 degrees, and angle P would also be 50 degrees. So because these two are both inscribed angles and they both intercept the same arc, they must be the same size. So the inscribed angles intercepting arcs conjecture says inscribed angles that intercept the same arc are congruent. So if I was going to mark that on this picture, you can see all three of these inscribed angles are intercepting this red arc AC. So corner D, oops, let me get a better pen mark there. Corner D is going to be the same size as corner B and the same size as corner F. That's because they all connect to this intercepted arc here. They're all inscribed angles. All the vertices are touching the edge of the circle, and they all connect to that same arc measurement. All right, the next one, inscribed angles in a semicircle. Now remember, a semicircle means it is half of a circle. So this arc right here is our semicircle, and that has to be 180 degrees because it is half of the circle. So what is AB? Semicircle that equals 180 degrees. Oh, I guess that's right here, 180 degrees. Inscribed angles are half the size. So if I'm looking at the inscribed angle, let's say ADB, that angle has to be half the size of 180. Well, half of 180 is 90 degrees. So I could put a 90-degree box in this corner. Now, because I have another inscribed angle, AEB, that is touching that same semicircle, that one is also a 90-degree corner. And finally, we have one more inscribed angle, AFB. Oops, got a little excited there. That one is also touching our semicircle. So it is also half the size of that 180 or 90 degrees. And again, because each of these inscribed angles is touching the same intercepted arc, they have to be the same size as each other. So this last one says they are all 90 degrees. All right, angles inscribed in a semicircle conjecture. We're just putting this into a formal conjecture now. So anytime you have an angle inscribed in a semicircle, so that would be this angle here, this inscribed angle, and I know that it's in a semicircle because it is being connected with a diameter, and that diameter is certainly going through the center, so I know that this is halfway across the circle. But anytime we have an inscribed angle in a semicircle, it is going to be a right angle. Excellent. All right, investigation number 4, cyclic quadrilaterals. So a cyclic quadrilateral is when we have a 4-sided polygon that is inscribed in a circle where all 4 corners are touching the edge of the circle. So that means each of these side lengths are chords in the circle. So this again is called a cyclic quadrilateral. So when I'm looking at a cyclic quadrilateral, the properties here, they don't have to be specific 4-sided shapes. It doesn't have to be a square or a rectangle or a kite. It can be anything with 4 sides. The opposite corners of a cyclic quadrilateral will always add up to 180 degrees. And the word for meaning adding up to 180 degrees is the word supplementary. So I'm going to write this out using this diagram as an example. Angle A plus angle C would equal 180 degrees. Angle B plus angle D would also equal 180 degrees. But it has to be the opposite angles. It is not the adjacent or consecutive angles. That, of course, if it was a square or a rectangle in there, that would be the case. Some other shapes as well, but it does not have to be. Okay, investigation number 5, arcs by parallel lines. Grab a highlighter here. So we've talked about all of these words here. The first one we talked about was radius. That starts from the center and goes out to a point on the circle. Then we talked about chords next, I think. Those are segments as well, but they connect 2 points on the circle. Then we mentioned diameter, and a diameter is in fact a chord, but it just has to go through the center of the circle while it's connecting those 2 points on the circle. And then we talked about tangents, and tangents are the ones that skim the surface of the circle, only hitting the circle one time. Our new term here is the term secant. And a secant is a line that crosses through the circle in 2 points. So it's kind of like a chord, but it doesn't start and stop at the circle. It continues on outside of the circle. All right, in the following picture, we have 2 secants. So here's one secant, and here's another secant. And it says these secants are parallel. So what I'm going to do is I'm going to take my pen and I'm going to use those little arrow symbols to mark that they are in fact going in the same direction. Okay, now if I look at those 2 parallel secants, what do you notice about the arcs that are between the 2 parallel lines? Anytime we have arcs between parallel lines, again, that's between them, they are going to be congruent in size. So here you can see this blue arc on the left is 40 degrees and this blue arc on the right is 40 degrees. And that's because if you were to take a ruler and set it across a circle, that ruler has a specific width. And so the portion of the circle or the arc that we're looking at would be the same in both cases. All right, that's it for our lesson. Here are your summary questions, and we will go through those together as a class. Thanks so much.